So exponential functions. There's a few things to think about when you're graphing an exponential function. First of all, to be an exponential function, it should look like this. Some number raised to the x power. It's exponential because the variable x is in the exponent. A couple requirements for the base when we're graphing exponential functions. The base does need to be positive. Thank you. And the base shouldn't equal 1. Why not equal to 1? Well, if you have 1 to any power, it's just 1. So it's not really an exponential function. It's a constant function. And why do we need to be greater than 0? Because if it's less than 0, we run into problems. 0 to negative numbers to a power aren't always very nice. Like -9 to the 1/2 power, that's the square root of -9. And that doesn't equal a real number. So we're going to limit ourselves to having positive bases that aren't 1, because then everything will look relatively decent. And there's a few things to consider. Thank you. When graphing an exponential function. So let's think about graphing something like y equal to 3 to the x. And although we're not always going to do this, I think the first couple times it does make sense to plot a few points. So I'm going to pick some real easy ones, like if x is 0, 3 to the 0 is 1. If x is 1, 3 to the 1 is 3. If x is 2, 3 squared is 9. And if x is -1, you get 1/3. There's just a few points we're going to plot. And here's what they look like. So I get x being 0, y being 1. When x is 1, y is 3. And already things are getting big very fast. I probably can't even really nicely plot the point 2, 9. I'm also going to have the point -1, 1/3. Be about there. And here's what it's going to look like. As the x values get larger and larger, the function gets exponentially large, right? It gets really, really big. As the values get more and more negative, the y values get smaller and smaller and smaller, but still positive. It's going to look like this. And there are kind of 4 things I usually think about when I'm thinking about how, I forgot to put my, sorry, I know it's not super important, but I just feel like it's important for the people on Zoom to be able to see my face. Maybe that's just because I'm vain. Maybe it's just because I'm weird. No, sorry, down here. I'm not really particularly vain. That's not true. I'm completely vain. My wife would tell you that I am a vain person, but she's wrong. Anyway, welcome, Malik. Come on in. So, hi, people on Zoom. As far as what to think about when you're graphing an exponential function, there are kind of, really there's only 2 things to think about, but there's 2 other things we want to make sure we don't mistakenly think about. So, if it's a basic exponential function, it hasn't been shifted, transformed, reflected, anything, it's just something raised to the x power, we have a y-intercept, and it's always going to be at the point 0, 1. If your power is 0, anything raised to the 0th power is equal to 1. I should say any base that meets these requirements raised to the 0 power is equal to 1. And then I also like to just clarify that there is no x-intercept. This graph never touches the x-axis. We do, however, have a horizontal asymptote. And it is at y equal to 0. So as this graph specifically moves further and further and further left, the y values get closer and closer and closer to 0. That's what it means to have a horizontal asymptote. You move way away in that direction, or way away in that direction. If the function is getting closer to a particular value, we call that value the horizontal asymptote. And then lastly, there is no vertical asymptote. Sometimes when you graph these, it kind of looks like you might have a vertical asymptote because it's getting very, very, very steep. We don't have a vertical asymptote because to have a vertical asymptote, you have to have a place where the function is kind of undefined. And this function is never undefined. You can always pick any value of x you want and plug it in. You just get a very, very, very large y output. And then a couple other things to note. Oh, what happened? How did I do that? Thanks. Where can you, thank you. Oh my goodness. How the heck, what is going on? Oh my God. Okay. It's okay. I know, it's because I turned it upside down. Wow. Okay, fun times. Yeah. Thanks. I like your, thank you. Thank you so much. Thank you. Okay, let's make sure I don't screw things up again. Let's put the mouse over here. Thank you. All right. Whew. Exciting times in class. A few other things to be aware of. This function is always going to be increasing from left to right, just meaning the y value is getting larger and larger and larger. It's going to be increasing if the base is greater than 1. And it's going to be decreasing, which we'll see on the next page, if the base is between 0 and 1. And the only other thing I think you kind of want to be aware of is that if the base is larger, the graph is going to be steeper. If the base is smaller, the graph is going to be less steep. So if we were going to graph, for example, y equal to 4 to the x, well, I'm just going to plot a couple points, really. If x is 0, y is 1. If x is 1, y is 4. If x is -1, y is 4 to the -1, which is 1/4. So instead of getting the point 1, 3, I get the point 1, 4. And instead of getting the point -1, 1/3, I get now, and this is where the graphing gets kind of dicey because right, like things are going to be very small. I get a point that's slightly smaller because 1/4 is a little bit smaller than 1/3. So what happens is this other graph is below 3 to the x over here, and then they cross at the y-intercept, and it's bigger over here. But when I think about an exponential graph, I think about having this shape. It goes up from left to right very steeply. And my hand is not the best hand for this, but if you look at your right hand, everyone's going to see my right hand very closely. You can kind of think about an exponential function being this line that many of us have on our hand up there. The reason I point this out is because we're also going to think about, my hand is really like someone else. I should have one of you come up and be like, here's a nicer hand without so many lines on it. Someone else, you can see there's also going to be a logarithmic graph kind of there. So if you look at your right hand, right, if you're right-handed, put down your pen, look at your right hand, and be like, oh yeah, there's some graphs there. I can see lots of nice lines on your hand. Like, oh yeah, that was perfect. But mine, maybe not so good. So if you're taking a test, right, what does an exponential function look like? Oh yeah, it's on your right hand. Don't look at your left hand. That's going to be some horizontal reflections on your left hand. And then we have the logarithmic functions. And the thing about the logarithmic functions is they are the inverse functions, which I know we haven't talked about yet. That's a later class, but we can still say those words. The logarithmic function undoes what the exponential function does. They interchange the values of x and y. So for example, if we were going to graph y, and I'm going to use all the space over here because I don't need it. Log base 3 of x. Instead of my inputs being 0, 1, 2, and -1, and my corresponding outputs being 1, 3, 9, and 1/3, they're going to switch places. Now I'm going to plug in values that are nice powers of 3. For example, if I plug in x equal to 3, what's log base 3 of 3? I know you guys know. 1, because 3 to the first power equals 3. And if x were to be 9, what's log base 3 of 9? 2. 3 squared is 9. And let's pick a couple more. If x were 1, log base 3 of 1 would be 0. And if x were 1/3, log base 3 of 1/3, you could either just say it's -1, because 3 to the -1 power is 1/3, or you could use your logarithm rules for the log of a quotient. Say that's equal to log base 3 of 1 minus log base 3 of 3. And that's equal to 0 minus 1. I know, it's fancy. So let's plot these points. I've got the point the point, x is 1, y is 0, x is 3, y is 1. I don't have enough space to get to 9, and 9's too far because I made my thing too big, so I'll just go down. And then x is 1/3, y is going to be -1. So I've got these points doing this kind of thing. And it's going to do this as well. As x gets closer and closer and closer to 0, the logarithm of x gets more and more and more negative. For example, if you picked a very small number, like I'm going to pick 1/81, which is very, very small. I mean, in the world of things, it's still not that small. Log base 3 of 1/81 is going to be -4, because 3 to the -4th power is equal to 1/81. So we can see that as the x values get really, 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 really close to 0, but still positive, the y values get super duper negative. Meaning we're going to have a vertical asymptote at 0, because the y values are getting as negative as you want them to be, or as negative as they can be as x is getting closer to 0. That's a good question. So why is log base 3 of 81 equal to -4? Sorry, log base 3 of 1/81. Well, one way we can say it is it's because this base to that power, if I want to find 3 to the -4th, the first thing I usually do is I rewrite it as 1/3 to the +4th. And then 3 to the 4th is 3 times 3, which is 9, times 3 times 3, which is 9, and 9 times 9 is 81. So that's a 1/81. So whenever you're taking a log of like a 1 over something, you're usually getting a negative number out, because you have to raise that base to a negative power to make it kind of a super small number. This is the typical shape of a logarithm. And again, just like the exponential function, it's going to have some kind of common hallmarks. The first of them being it's going to have an x-intercept at 1, 0. It's not going to have a y-intercept. It's going to have a vertical asymptote at x equal to 0. And it's going to have no horizontal asymptote. And although you could have a base that is between 0 and 1, it's pretty atypical. So usually for a logarithm, although right, the base can be any positive number except for 1, we almost always limit ourselves to bases that are like 2, 3, 4, 5, etc. The nice positive integer numbers, with one notable exception. The natural base e, which is approximately 2.7. These are the typical bases you will see for logarithms. It's not that you couldn't have a log base 1/3, it's just that we usually don't. Oh yeah, question, bro.
So for all of those bases, 2, 3, 4, 5, 6, would it also have the x at 1, 0?
Yes, exactly. For any base, the x-intercept is going to be 1, 0, because, well, if we take, for example, pick your favorite large number. I'm going to pick 8. If I take log base 8 of large, I mean, okay, fine. Log base 8 of 1, that says 8 to what power equals 1? What's the power got to be? Right, it's got to be 0. 8 to the 0th power is 1. If it was log base 8 of 1/8, that's when it would be -1. So whenever you plug in 1 to a logarithm, you get 0 out. Just like whenever you plug in 0 to an exponential function, you get 1 out. And so something I'd really like everyone to see here is literally for this logarithmic function and this exponential function, all of the x and y things have interchanged. Here I get an intercept at 0, 1. Here I get an intercept at 1, 0. Here I get no x-intercept. Here I get no y-intercept. Here I have a horizontal asymptote at y equals 0. Change y to x, you get a vertical asymptote at x equals 0. Here no vertical asymptote. Here no horizontal asymptote. So all the x and y things for these inverse functions are interchanged. Yeah. And then I will point out, if we were going to graph something with a larger base, like log base 4 of x, I'm just going to plot a couple points. What's one point I definitely know I get? 1, 0, right? We know that's true for every logarithmic function. And what's the next biggest number that's easy to plug in for x? Well, here, go ahead. Well, you're not wrong. But log base 4 of 2 is a little more work than I want to do. Because 4 is the easier one, right? What's log base 4 of 4? Right. So if I plug in 4, I get out a value of 1. This one's just a little bit more gradual. And they do cross here. Like that. So there's y equal to log base 4 of x in green. And there's y equal to log base 3 of x in black. So what we see for logarithms is the larger or the smaller the base, the steeper the logarithm. And the bigger the base, the shallower the logarithm. Or another way to think about it is the logs with the bigger bases grow less quickly because x has to be much larger to get a bigger output. Right? Here, x had to be 4 to get 1. Here, x had to be 3 to get 1. All right. So what I want you to know so far, exponential functions have this shape. They increase very, very quickly from left to right. Logarithmic functions have this shape. They do increase forever, right? They keep getting bigger and bigger and bigger. They just do it very slowly. Yeah, is there anything else I want to say on this page? Yeah, a couple of things. The last things I want to say before we move to the next page is for exponential functions, the domain is all x values, all real numbers. The range, you get all positive numbers. So the range is y has to be greater than 0. And just like everything else, the x and the y things are going to switch. So here, the domain being all reals means over here for this function, the range is going to be all real numbers. And here, the range being all positive numbers means the domain is going to be all positive numbers here. So over here for this logarithmic function, the domain is x greater than 0. And the range is, even though it doesn't look like we're going to get big very fast, and we're not, this function does get infinitely large. It just takes a super long time. So when you're thinking about an exponential function, you should think about this shape and specifically these facts. If there's a y-intercept at 0, 1, there's a horizontal asymptote at y equals 0. And then for a logarithmic function, you should be thinking about this shape. And there's an x-intercept at 1, 0, and there's a vertical asymptote at x equal to 0. Those are kind of the real salient points. Yeah. What is an asymptote? Exactly, a very good question. So there are 2 different sorts of asymptotes. Well, actually, that's a lie. There are more than 2 types of asymptotes. There's also something called a slant asymptote. But right now, we're just talking about these 2 types of asymptotes. So an asymptote, a horizontal asymptote, is a value that the function gets closer and closer to as you go either out towards negative infinity or out towards positive infinity in the x direction. So if I go way, way, way to the right, nothing's happening way, way, way to the right. Or I should say, we're not getting close to one particular number. Right? This function is just getting larger and larger and larger. But if I go way, way, way to the left, this function gets very, 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 very small. It gets very close to 0. So because the function is getting closer and closer to 0, we say y equals 0 is a horizontal asymptote. And then we have a vertical asymptote here, which is saying as x is getting closer and closer and closer to the vertical asymptote value, which is x equal to 0, this function is getting very, very, very negative. So when you have a vertical asymptote, the function either gets infinitely large or negatively infinitely large. When you have a horizontal asymptote, as you go out way far to the left or way far to the right, the function gets close to a particular number. One way people often think about vertical asymptotes, although it's kind of weird for logarithmic functions are kind of like the special exception for vertical asymptotes. Later on, when we talk about rational functions, which is in a few classes, we'll see that You usually get a vertical asymptote when a function is being divided by 0. That's kind of not the case here, though. So what I would encourage you to think about for now is that for a logarithmic function, we know we can't take the log of 0. Well, do we know that actually? Maybe we should say that for a second. Why can't you take the log of 0? That's a good question. Why can't we take log base 2 of 0? Well, let's try it. How do we usually deal with a logarithm? We said, whoops, that's a 0 there. We set it equal to a variable like y or x. Okay, I'm going to rewrite this. What's my base? What's my power? What's it equal to? Does 2 to the y ever equal 0? No, I mean, look, right? Not that this is 2 to the y, but you could graph 2 to the x like that, and 2 to the x would never, ever, ever equal 0. So this has no solution. So we can't take log base 2 of 0. And the same is true for a negative number. If you want to take, say, log base 3 of -9 and try and solve that, it doesn't work. 3 to the x equals -9. There is no power on x that makes it equal to a negative number. You might be thinking, James, it could be -2. And I would tell you that 3 to the -2 is 1 over 3 squared, which is 1 over 9, which is not -9. So this also has no solution. No solution, no solution. So we can't take logs of 0 or negatives. And so when I'm graphing a logarithm, usually I think about the first place where it can't be taken as where you get the vertical asymptote. So essentially, the idea I would like you to keep in mind is that when we're graphing log of x, 0 is a problem. And that's where we're going to have the vertical asymptote. And then anything to the left of 0 is totally off limits. Right, this graph doesn't exist over here. Questions? Mm-hmm. So for here, the domain is x is greater than 0. Yeah. Domain is always what we think about the inputs, the x values being. Y is always what we think about. I mean, yes, but the rule really is because of what we just said, right? We can't, like we're graphing y equals log base 3 of x. We can't plug in 0 because it doesn't work. Right. Yes, exactly. Other questions? You guys are asking good questions. Keep them coming. Or don't, like it's also fine. You got more pages to look at. Although really the rest of the pages are just more examples of graphing these things. With a couple twists, a couple transformations. Of course, we're going to transform them. They're more than meets the eye. Nobody, okay. It's all right. It's all right. So let's graph y equals 2 to the x. And here's where I don't want to really have to be super precise. Like if I ask you to graph y equals 2 to the x, here's all I really want. I want that point. I want the horizontal asymptote. And we know there's a horizontal asymptote. And y equals 0. And then just the right shape. It should go up like that. Now I am going to graph it precisely so that it doesn't look terrible. But really, if you were graphing this, you should be like, okay, James, it's going to do that. And it's going to go up to the right. Now, I know I'm going to get some points there, and there, and there. There's my y equals 2 to the x. Yes, I plotted some points. I plotted the points 0, 1, 1, 2, 2, 4, 3, 8, and -1, 1/2. Those are the points I thought about graphing when I was graphing this thing. But I'm saying is if you were graphing this on your own, really, here's what I want to see when you graph something like this on your own. There's my y-intercept at 0, 1. And there's a pretty good graph. I'm sorry, you guys can't see that real. If I was graphing y equal 2 to the x, that's what I would really do. There's not a lot of other information you need to include. In fact, I guess there's one thing I should say. There's a horizontal asymptote at y equals 0. And hopefully I'm making it relatively clear that I'm not asking you for tons of detail with the graphs, right? I want you to get the right shape, the right transformations, but it doesn't have to be like every single little point. It shouldn't be. That's not a great use of your time. Question? Oops. Question?
How this sounds rudimentary.
Hit me with it.
How did you know it was a horizontal asymptote?
So because,
It's exponential?
right, exactly. Because it's an exponential function, right? So what we want to take to heart from this first page here is that every exponential function looks like this. It always is increasing from left to right. It always has a horizontal asymptote at y equals 0. Until we maybe start shifting it or stretching it or doing whatever. But at the very base level, always going to have a horizontal asymptote at y equals 0. Go ahead though, you were saying something else?
I was just gonna say like the second example is gonna be more.
You mean this example here?
No,
On the next page, yeah. Yeah, exactly. This one also is going to also have a horizontal asymptote. Now, this one's going to be a little bit different because our base now is smaller than 1. So what's happening here is that when you plug in x, as x gets larger, 2 to a bigger number is a bigger number. Right? 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, and so on and so on and so on. Whereas here, if the power gets larger, 1/2 times 1/2 times 1/2 is a smaller number. So every time x is bigger here, the output's going to actually get smaller and smaller and smaller. So what we're going to see here is that if x is 1, y is going to be 1/2. And if x is 2, 1/2 squared is 1/4. And I can't really graph it much better than that, but as you go to the right here, it's going to get closer and closer and closer to 0. It's not ever going to equal 0 because 1/2 times 1/2 times 1/2 times 1/2 as many times as you want is still a very, very small positive number. But as we go to the left, it's going to get bigger. What's 1/2 to the 0th power? 1, right? It's all right. If I say something to the 0th power, we know the answer is 1. Okay, what's 1/2 to the -1? So there's a couple other ways we could think about this. Let me show you two things. If I want to rewrite this, I could totally rewrite this as y equal to, I'm going to write 1/2 as 2 to the -1. And then when you have a power to a power, what can you do with those powers? So -1 times x is just -x. That's 2 to the -x, which is just like 2 to the x, except it's got what kind of reflection? Across the x-axis or across the y-axis? It's across the y-axis. So we're taking this graph here and we're literally just flipping it over like that. Meaning it's going to look like, I'm going to cheat a little because I want it to look nice. It's going to look like that. It's just that graph flipped over the y-axis. I wouldn't say it's the inverse of the first one. I'd say it's the reflection of the first one. Yeah. You could also have plotted some points, right? Plotting the point, again, I don't want to keep modeling plotting points because that's not what I'm trying to tell you to do. I could totally plot points, but like, I really just want to be like, if the base is less than 1, it's going to decrease from left to right because we know it's going to get smaller and smaller and smaller as x gets larger and larger and larger. So when your base is between 0 and 1, this is the typical shape. Decreasing from left to right. I don't really need to include the left to right part there. Whenever someone says something is decreasing, they always mean as you move from left to right, it's getting smaller and smaller. Whenever someone says the function is increasing, they always mean as you move from left to right, it's getting larger and larger.
So if the question is asking us to graph like y equals 3 to the power of x, would we just graph it the same? Like we just put the y-intercept and just the exact same shape.
Yes, exactly. That is exactly what I'm trying to say. Yeah. And now, so let's say you don't love that, right? Like maybe like James, I would love to provide just a little more detail on my graph because that seems just, I don't know, it feels not perfect to me. Here's what I would encourage you to do. I need to bring more paper to class. I always forget to bring paper. Let's say we wanted to just graph y equals, let's say 5 to the x. Here's what I would do. Here's what I would want you to do. Here's my XY coordinate system, and we know we're going to get the point 0, 1. Okay. And if you're not feeling like that's enough detail, you can throw in another point there. Where what's the next easiest point to plot? X is 1 and y is 5. Now, is my graph to scale? Probably not. Is that okay? Definitely. So that's really, I mean, that's all there is to see with this graph, right? There's not a lot. I guess I should also point out, and there's a horizontal asymptote. Y equals 0. That's kind of all the detail I'm expecting if there aren't any shifts or transformations. Other questions? Okay. So, base larger than 1, increasing from left to right. Base smaller than 1, decreasing from left to right. So I guess I should say, in that same vein, if I asked you to graph something like, I don't know, y equals 3/4 to the x power, I know that this function, oh, there's also a piece of blank paper on the last page of this thing in case you're, right, like there's extra paper for you to write on, which I guess I have too, which I didn't really think about. Okay, well, that's, you know, sometimes you're not always smart. Anyway, so this base, my base here is definitely less than 1. So I know that this is going to be decreasing from left to right. I'm still going to get the intercept at 0, 1, and then it's going to look something like this. Still has a horizontal asymptote at y equal to 0. Still has the point 0, 1. And you could include more points if you felt like you had to, but you don't have to. Erica. You could write it as 4/3 to the negative x. So this is also equal to, room. You could write this as y equals 4/3 to the negative 1 to the x. Because 4/3 to the negative 1 is 3/4. And then you could rewrite that as 4/3, which is a positive base, but now it's to the negative power. So it's taking your usual increasing from left to right shape and reflecting it. And then if you wanted more points, you could plot more points. Like if x was equal to 1, you would get the point 1, 3/4. Or if x was equal to negative 1, you get the point -1, 3/4 to the negative 1 is 4/3. You don't need to plot these extra points, but I can see how if you wanted to plot them, they might make you feel more comfortable with having provided quote unquote enough detail. Okay. So then we do the usual garbage and we move things around. So now I want to graph something like this. F of x equals 4 to the x plus 1 minus 5. So let's start off with the base graph, the 4 to the x. And I am going to plot all the things just to show you all the things. Yeah, we got time. So here's what 4 to the x would look like. It's going to hit the point 0, 1, hit the point 1, 4. It gets steep super fast. All right. If I add 1 up there, which way we shifting? Up, down, left, right? I think it's left. So I don't actually like, is it right? I think it's left because right when you add on the, so here's what we're doing. Although maybe you might not see it as the quote unquote inside. Here we are adding 1 to x before we are raising 4 to that power. So if I was thinking about y equals 4 to the x plus 1, we're kind of adding 1 first and then doing the power later. So we're doing something inside the function, which does affect it horizontally. But remember, the shifting horizontally is always kind of counterintuitive. If you're adding, you have to shift to the left to counteract the adding that you did. So this is going to shift it 1 to the left. And now this point 0, 1 is going to become the point negative 1, 1. And this point 1, 4 is going to become the point 0, 4. These graphs shouldn't cross each other. That's what that one looks like. I should probably fill these in. They look, I was like, maybe they'll look better if I draw them dashed. They don't. You don't need to draw the intermediate graphs. I'm just trying to show you what things look like. And now what's the -5 going to do for us? Yeah. Down 5. That was going to be. Okay, so I'm going to take this point that I know, right, was at 0, 1, moved left 1 to negative 1, 1. Now that's going to move down 5 to negative 1, negative 4. I do like to think about where that initial kind of y-intercept point moves to. And then also this point happens to be on the y-axis. It's going to move down 5 as well. So I've got this. Something else moved down 5. These graphs both have a horizontal asymptote of y equals 0. That horizontal asymptote is going to move down the same amount. So my new horizontal asymptote is going to be y equals negative 5. And we do have to draw it. So there's my y equals 4 to the x plus 1 minus 5. So when we're drawing this, if you were drawing it without doing the intermediate steps, I would be thinking, okay, I'm gonna take my graph and move it to the left one, down 5. One sec. Try and draw it there and then kind of put in the important details. Yeah.
So why does the order matter? Like, why couldn't you put down 5 first and then?
You totally could.
Okay.
So if you're just dealing with shifts, you can do the vertical shift and the horizontal shift completely kind of separate from each other. It doesn't really matter which one you do first. It's just, we typically kind of do, I like to think of it as working from the inside of the function out. So I'm kind of looking at what's happening to x and kind of moving away from that x as I look at all the different transformations. But if something else is working for you, that is totally fine. Like if you want to do the shift down first and the shift, really, I mean, honestly, I'm kind of thinking them both at the same time, but I can't do two things at the same time. So I'm showing you one, then the other. Christian. Yes, specifically reflections and shifting. The order definitely matters there. So we have to be super careful when there's a reflection and a shift of the same sort of type. So if there's a horizontal shift and reflection, you have to pay attention to the order. If there's a vertical shift and a vertical reflection, you need to pay attention to the order. And I think I have an example down on this page. I don't, but I could. So the last thing I'll say is we've shifted this around and now there are some intercepts. There is an x-intercept now. There wasn't before. There is a y-intercept. There was a y-intercept before, and we should find them. So how do I find the y-intercept? How do I ever find the y-intercept? Set x equal to 0. If I set x equal to 0, y is going to be f of 0, which is 4 to the 0 plus 1 minus 5. So that's going to be 4 to the 1 minus 5, which is negative 1. And in fact, if I had been smart about this, I probably would have done this before I graphed it. I'd be like, where's the y-intercept going to be? Oh, it's going to be at negative 1. And the x-intercept is going to be probably not as nice. To find the x-intercept, we set y equal to 0. If I set 0 equal to 4 to the x plus 1 minus 5, we're going to add 5 to both sides. And if I was trying to solve for this, we'd have to use logarithms. So I would take the natural log of both sides. Natural log of 5 equals the natural log of 4 to the x plus 1. I'm running out of room. I go over here. The x plus 1 comes down. And then then we're like, this is not great. Then we divide both sides by natural log of 4. And then we subtract 1. And the bummer about this is sometimes your intercepts are just gross. Is this useful? Not really, right? Did that help us graph it? No. Did knowing would it have been helpful to have known this before we graphed it? Yeah, it would have been. So the intercepts, although we should be finding them because people want to find them, the x-intercept here is gross. I wouldn't have found it. I would have just been like, there it is, there's my graph. So if the x-intercept seems like it's going to be terrible, leave it alone. On the other hand, I'm going to show you an example where the x-intercept is not terrible. So let's take a look at that. We got time. Okay. It's always a struggle for time. So let's look at this graph. N of t is 2e to the negative t minus 2. I see some shifts, some transformations. The first one being, I see a horizontal reflection. Because of that negative. So we know after the first transformation, it's going to look something like that. What's the 2 going to do out? So what's the 2? Which 2? What's this 2 going to do for us? It's going to stretch. It's going to stretch it vertically, which I don't love. But here's the one thing I can see. Instead of getting the point 0, 1, if I'm graphing y equals e to the negative t, if I then stretch it by a factor of 2, now, instead of plugging in 0 and getting 1, I'm going to plug in 0 and get 2 times 1. So it stretched it up by a factor of 2. I know my graphs don't look very different. They don't look very different, to be honest. Like they're not that different. But this one is further away from the y-axis than this one. And then finally, we're going to shift this down too. So it looks like, although before I actually do the graph, it looks like if you put this down too, I'm going to hit the origin as one of my points. But before I actually get that, instead of trying to like make the graph happen, I'm just going to find the intercepts instead of trying to graph the thing first. So if I find the y-intercept, I'm going to set t equal to 0. And n of 0 is 2e to the 0 minus 2. And yeah, that's going to be 0 because e to the 0 is 1. And 2 minus 2 is 0. So there's my 1 point I know. And let me ask you all, what's my horizontal asymptote going to be? You guys are all saying very plausible things. So normally, if we hadn't shifted it up or down, what's the usual horizontal asymptote? 0, 0. How much are we shifting it down? 2. So if I went from 0 down 2, it's got to be negative 2. So the new horizontal asymptote is always just going to be however much you've shifted up or down. So if you were at y equals 0 and you shifted up 3, the next one's going to be y equals 3. If you were at y equals 0, which you're always starting at, and you shift it down 2, the horizontal asymptote is going to be y equals -2. And then I'm just taking this graph here and I'm shifting it down too. So it's looking kind of like that. Is that perfect? No, not at all. Is it good enough? Yes, it's definitely good enough. Is there anything else I want to say about this graph? Not really. Yeah, not really.
I don't really know how much curve to give it.
That's the terrible question to ask, meaning it's a great question and I don't have a good answer. So if you wanted to draw this graph very accurately, here's what I would probably do. I would probably plot another point. So if I wanted to make this more accurate, and this is where things are terrible if your base is E, you'd be like, well, James, what if you plugged in t equals -1? If t equals -1, then n of -1 is going to be 2 times e to the first minus 2. And then you would need a calculator. That's not true. We know that e is about how much? So 2 times 2.7 is 5.4. Minus 2 is about 3.4. So if I was really trying to make this graph look more accurate, I would have plotted the point -1, 3.4. See how not accurate my graph is? That's okay. So really, I would say don't sweat the curve. Like, I mean, you want it to be nice, but if your curve is not as curvy as it needs to be, that's okay. Yeah, we don't need to be super accurate with these. Can you say that one more time?
The curve will be steep here because of expression.
Yeah, it's interesting because the vertical stretch actually doesn't actually really affect the curviness of the curve. It just kind of affects, like, it kind of looks like it's curvier here when it would have been over here. So it's kind of interesting. Like so here's where I would make a plug for using the tools you have available to you, right? Like I would definitely, if I were a student, graph these things on Desmos and compare them. Like I think it's definitely worth your time to be like, how does e to the -t versus 2 times e to the -t actually look? And get a really good idea of that because, oh, sorry, you can't see that. I would kind of maybe see if you're curious, right? Like this is a good time to, I know you guys don't have all the time in the world, but like if you have a moment to see what these kind of things look like differently, I would encourage you to look at them. Yeah.
Will these functions be on the quiz?
These functions will not be on the quiz today. Yeah. I usually try not to have the quiz be on the material that we talk about in class on Friday because that doesn't seem particularly fair. Okay. We got a couple minutes. We should definitely look at this last example. So log base 2 of x plus 4 minus 2. So I see a typical logarithmic graph. Here's my typical logarithm. Y equals log base 2 of x. And you're totally right. You could totally do either shift first if you wanted to. I'm going to do the horizontal ones because that's what I see. I'm going to shift this 4 in which direction? To the left, right? Because now x can be -3. And -3 would be totally fine because -3 plus 4 is still positive, and we take the logarithm of a positive number. The first x value that's quote unquote bad or not in the domain is -4. And -4 is where our new vertical asymptote gets to live. Because we've shifted it 4 to the left. Our old vertical asymptote would have been at x equals 0, but now we've subtracted 4 from 0 and gotten x equal to -4. And then we're going to shift it down to, seems like a cop out. Not on your guys' part, on my part, it seems like a cop out, but we shift it down to, well, again, I know what the shape looks like. The up and down shifts for the vertical, for the logarithms are kind of like, they don't visually seem as like significant. Right? When you shift a logarithm left or right, you're like, oh yeah, I can really see that. You shift it up or down, it's kind of like, well, I can kind of see that. So before I do the up or down shift, that's how I would start thinking about what are my intercepts. So since I've shifted this thing to the left, I know I'm going to have a y-intercept. If I set x equal to 0, we're going to get y equal to log base 2 of 0 plus 4 plus, sorry, minus 2. Oh, that's terrible, James. The big minus sign. And I know we should wrap things up here. What's log base 2 of 4? And 2 minus 2 is 0. So we end up getting the origin again because somebody who wasn't me designed these problems to be a little too easy, I feel like. So here's what our shape's going to look like. That's probably not super accurate. It's definitely not super accurate because I know that -3, -1 is actually a point on this. Or sorry, -3, -2, I apologize. So it's okay to not be 100% accurate all the time. As long as the shape looks right, as long as you've got the intercepts, at least the ones that aren't super terrible, that's what you should be shooting for with these graphs. But really, really mostly the shape and the asymptotes. Those are like the big things for these graphs. The shape and the asymptotes, the rest of the stuff, not so much.